Hi everybody, here is our convergence video. This video is going to summarize what Mr. Siddiqui did with you at the Saturday session. He introduced 4 of the convergence tests with you. We have 2 more to do. So I know some of you wrote some stuff down when he was going over the session with you. Some of you didn't write much down. I want everyone to write down the summary here. This cuts out some of the extra stuff you were talking about and just summarizes the main points with like 1 or 2 examples of each. That way it's all organized and neat in your notes, and then you can add 2 more on, and then they're all together. So here are some general guidelines that you can use whenever you're doing convergence testing. The first thing that you should always do whenever you're given a series and you want to see if it converges or not is you should use the nth term test. So this is going to see if it's even a candidate for convergence. Now, this is only used to prove divergence. So if you do the nth term test and you see that it diverges, then you can't even try anything else because you're done. If it doesn't diverge, it's a candidate for convergence. It doesn't prove it converges. So once that it passes the nth term test, the next thing you should do is see, is it one of the special cases that are quick and easy? P series is the quickest. A harmonic series is a special case of the P series. It's when P is 1, so your exponent here is 1. Remember the P series was 1 over n to the P. You can also want to see if it's an alternating series. This test we have to go over a little bit more. Or you should see, is it a geometric series? A geometric series is when you have a sum of numbers and they have a common ratio. If that common ratio is less than 1, then it converges. And you can actually see what it converges to. Remember this is one of the first things we did. It was the sum of an infinite amount of numbers. So if it's not one of the special cases, then you should try and do the direct comparison test, which he did with you. See if it's similar to one of the above. Or, this is something we have to do still, the limit comparison test. I'll show you that this week. Now, if there is a factorial in it, you're going to want to try something called the ratio test, which we have not done yet. And if none of the above work, then go to the integral test, which he did do with you, which I'll do a quick review of. That's usually the last resort if nothing above works. So that's kind of your little roadmap for when you do these. So here's a summary of the test we did so far. Now we talked a lot, or he talked a lot with you about this series right here, 1 over n. Now keep in mind this one is harmonic. And what he did is he wrote them all out. He called us going whole hog whenever you write them out term by term. And then he talked about 1/2 to the n. And what he said is, look, these 2 series share some numbers. Are they going to converge or are they going to diverge? At first it seems like this series should converge because the terms are getting smaller and smaller. And in order to converge, we need to get to 0. Hold on, we need to get to 0 eventually as we go to infinity. And whenever he said the word eventually, he meant this. This plus dot 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 is what he referred to as eventually. As you keep going and going, you need to get a 0. You need to start adding zeros. He called this term the term as n goes to infinity. And then he called this term the Buzz Lightyear term because it's beyond infinity. And it's not enough for you to get to 0 here. You also have to go to 0 fast enough. So if you don't get to 0 fast enough, you're not going to converge, you're going to diverge. Eventually, we found out that this guy actually diverges because even though you do get to 0 here, it doesn't get to 0 fast enough. It has too many extra terms. This one does converge. It did get to 0 quick enough. It cut out some of the extra terms. So a quick recap of the nth term test, which we used above here. What you do is you take the limit as n goes to infinity of your rule or the generator, this thing right here. So if it does not equal 0, then the series diverges. If it does equal 0, you could converge. So if I do it right here quick, the limit as n goes to infinity of 1 over n. Well, 1 over infinity is definitely 0. It could converge. The thing is, it doesn't get to 0 fast enough, which we'll talk about when we do the integral test. 1/2 to the n, if I do the limit as n goes to infinity. 1/2 to the n is the same as 1 to the n over 2 to the n. Well, 1 to the n is 1 over 2 to the n. This would be 1 over 2 to the infinity, which is 1 over infinity, which is 0. So you do start eventually adding zeros here as well, and this one will diverge. It does get there fast enough. Moving on here, so there's the nth term test. I'm going to show you a couple real quick here, just to remind you of how this thing works. Now, he did these with you, but I don't think many of you wrote these down here. So write them down so you have them for your notes. Let's take this series right here, 2n over n plus 4. If you write it out, you get these terms here. Notice they are getting larger and larger. You go from something less than 1 to becoming more and more than 1. If you want to see what it does eventually, then you should do the limit as n goes to infinity of your generator. Now, this is the horizontal asymptote rule. If the degrees are the same, as you go to infinity, it's your coefficient over the leading coefficient, which is 2. So that means eventually you start adding a bunch of 2's, so that's obviously going to diverge. Right here, 3/2 to the end. As you start adding these up here, let's see if this thing converges. So eventually, that would be right here. That would be 3 over 2 to the infinity power. Well, that's obviously infinity. That means you add larger and larger and larger numbers. Definitely going to diverge. If you try doing n plus 5 over 3n minus 2, let's see what happens eventually. So I did the limit as n goes to infinity of the generator. Now again, this is the horizontal asymptote rule. As n goes to infinity, if the degrees are the same, it's leading coefficient over leading coefficient. That'd be 1/3. So that means the numbers get kind of small. They go to 1/3, but you're just going to keep adding 1/3, 1/3. It's not 0, so it diverges. Now right here, 5 over n cubed, to see what this thing does eventually. Notice these terms seem to get smaller and smaller, way smaller and smaller. Let's check to see if it could converge. So the limit as n goes to infinity, that'd be 5 over infinity, which is 0. That means eventually you do start adding 0, and all the other terms after infinity to the Buzz Lightyear term, you're going to keep adding zeros. So this guy could converge. So that's all the nth term test tells you, if it could converge or if it diverges. So now let's take a look at these two series here, 1 over n and 1 over n squared. These are two really important series, and they are a good summary for the integral test here. Now, he did this visual for you. He said, all right, draw Riemann sums for 1 over x. So what we did here is, let's do 1 over n first, this series. Let's turn our generator into the function 1 over x. And let's graph our function. I stopped at 6 because I didn't feel like drawing any more rectangles. We want to use a left sum here to make it larger than the actual integral value, which would be the area under the curve. And notice this series, which is 1 plus a half plus a third, etc., is actually this integral, this Riemann sum here. If you add up all the Riemann sum numbers, add up their areas, the areas of the Riemann sum are the terms in the series, so they're the same thing. So let's go ahead and do the improper integral and see what the actual integral does. Now the integral, remember, is the area right under the curve, and we are above the integral. So this is an improper integral. So let's do the limit as b goes to infinity. This is a quick review of improper integrals. So I have the limit, and you got to write this part over and over again. Antiderivative of x is ln of x, technically with absolute value bars. So it's the limit as b goes to infinity of natural log of b minus natural log of 1. Natural log of 1 is 0. So that means if I were to plug infinity in here, natural log of infinity does go to infinity. This diverges. So since the actual integral diverges, then our series, which is the Riemann sum, which is bigger than the divergent integral, definitely must diverge as well. Because the actual area goes to infinity, that means this sum is even bigger than infinity, so obviously diverges. And that's the summary right here. If the integral diverges to infinity, then the Riemann sum, which is the series, must also diverge, since the series is greater than the integral. So that is why 1 over n, the harmonic series, remember 1 over n is harmonic. That's why this guy converges. Even though the terms do go to 0, it passes the nth term test, it's still going to diverge. It doesn't get to 0 fast enough. All right, now let's take a look at 1 over n squared. The graph is really similar. It's just a little bit closer to the origin. It's a little bit steeper. So the series here is the same as the series above. It's just you cut off some of the terms in between. That eventually is going to mean that it goes to 0 faster, which is why this one's going to converge. But anyway, here, notice our terms here, 1, 1/4, 1/9, etc., are the actual values of the areas when we do the Riemann sum. And we want it to be less than the integral, so let's do right sums because we want it to be less to prove something here. So let's go ahead and actually do this improper integral. And the integral is the area under the curve here. And let's see what the integral does as we go to infinity, and then let's see how that compares to the series. So to do an integral, you need an x here, an actual function. Remember, he made the distinction. This is a generator. N is like the term number. We want an actual function. You need a function. What am I writing right now? You need the function to do an integral. There we go. Okay, so let's do the limit as b goes to infinity because it's an improper integral. And whenever I go ahead and do that antiderivative, that's x to the negative 2, so add 1, x to the negative 1 divided by negative 1. So that's the limit as b goes to infinity. Sorry, I'm getting a little messy here. Of negative 1 over x from 1 to b. And when I plug in here quick, that's negative 1 over b minus a negative 1 over 1. So if I were to plug infinity in here, even negative 1 over infinity will go to 0, and I'm left with 1. That means the area under the curve as you go to infinity and beyond is 1. So our integral converges. That means our series, which is the area of all these, must also converge because it's less than the area, which converges. So make sure you have all that down, pause if needed, and go right here. So if the integral converges, then the Riemann sum, which is the series, must also converge, since the series is less than the integral. Keep in mind here that every series can be written as an integral, which is why the integral test even works. So here's the integral test written out. So the integral test basically says that a series and its corresponding integral behave the same. So if the integral converges, the series converges. If the integral diverges, the series diverges. Now, we talked about 1 over x, and then, oh my god, and then 1 over x squared. So here was 1 over x, and then here was 1 over x squared. We want to make this more general for 1 over x to any power. That's what the p-series test does for us. The p-series test is a real quick, easy test to use. It's 1 over n to some power p. If p is bigger than 1, the series will converge. If p, which is the exponent, is less than or equal to 1, the series diverges. Remember, when p is actually equal to 1, that, once again, is your harmonic series. And then he talked about the integral test to prove this. So like when I did the integral of 1 over x squared, the reason that this thing converged is because when I did an antiderivative, x was still in the denominator. So I got that 1 over infinity here. Whereas whenever you did the antiderivative of this, x is no longer in the denominator. So that's why it diverged. So you want to write this down here. X must be in the denominator still to converge. All right, last thing here, then we're done. So I have a sum of 1 over n squared plus 10. When you first look at this, this seems like it should converge. It's definitely not a p-series, though, because a p-series must be in this exact form. And this has a little bit more going on. Well, if I compare this, this looks pretty similar to 1 over n squared. I know about 1 over n squared. It's a p-series, and it converges. Now, this is smaller than what I know. Because I'm adding 10, I'm dividing by more. When I divide by more, I get a smaller number. So if I have something that's less than something that converges, then it must also converge. That is the direct comparison test. This is different than the limit comparison test. We'll learn the limit comparison test this week. When you write this rule down, just keep in mind that k sub n is a known series, kind of like this is a known series. And g of n is a given series that I want to know something about, like this guy. So go ahead and write this down. And this here proves convergence and divergence for 2 of the cases. For 2 of the other cases, you have no info and you have to go to another test. So go ahead and get these notes written down. In class, we're going to practice these tests right here. Then I will add on the ratio test and the limit comparison test. So I'll leave this right here. And I'll see you tomorrow. Bye.